Gonna do that the whole time. Okay, we're good. All right. Okay. I'll give a brief introduction about kind of the project, the group, and then we're gonna have everybody kind of take their individual blocks, right? Come up, present their progress, right? The topologies and their results. So this whole group, which is everybody in this room, a lot of them have been your students. We're all members of IEEE, and recently we started a new kind of like technical committee within IEEE to focus on IC design. So within that, the primary interests are really on the RF side of IC design. So we're doing a 2-die system that'll be a software-defined radar operating at 24 gigahertz. So I have a very general block diagram, right, to kind of show the 2 dies that we're producing, and then also the components that will be on each one of them. Our RF front end on the right is being taped out on IHP SG13 CMOS 5L, which is the education version of SG13 G2. FT we characterize to be around 110 gigahertz, right? And we're using that for all of our 22 to 26 gigahertz bandwidth RF components. So mixer, phase shifter, PA, LNA, and we're also doing on-chip frequency synthesis with an integer N PLL. The GF180 chip is a slower but more affordable process. It's something like $400 per millimeter squared instead of 1700. And so we're using that for the more digitally sided blocks and also for our like signal generation. So instead of doing a stepped like PLL chirp for an FMCW waveform, instead of doing that, we're using a DAC and an ADC to do that fully digitally, which gives us a little more flexibility, and it also just makes the topology more capable, more interesting, and we can use it also as just a transmitter, or transceiver, I should say. Beyond that, I think the goal of this project is to really just validate blocks, right? Like all of our blocks are going to be isolated on the chip, right? Fully branched out to pads. And then to try and integrate like chains of components, we'll match and bond wire them externally, right? But that way, if, for example, the PLL doesn't work, right, which frankly is very possible, right, on a first tape out, we want to make sure that we can still effectively test all of the other RF components and get as much out of this tape out as we can. And the same thing does go for the GF180 side. However, like kind of the transmit and receive sides will be all connected together, and we'll only have like an external clock source just in case. So if you think I'm missing anything, I'll let Ryan take the floor and talk about his phase shifter.
Okay, thank you, Max. Hello, Professor, again. So I'm building the phase shifter. The topology that I chose is a phase rotator. It's pretty simple. You just split into IQ components, apply variable gain, and then recombine these two phases at the output to get your realized phase shift. And this is one of maybe 5 or 6 different topologies I looked into. The reason I chose it is because there's a minimal amount of inductors. The only problem is that instead we have to deal with transformers or balance. And the other benefits is that it's low loss and has a great tuning range. We can, in theory, tune over an entire 360-degree phase range. And we can do so with analog phase shifting as well. So instead of having like discrete digital phase shifting, we can technically achieve any phase shift we desire. In terms of requirements, we need a 14 decibel tuning range for the VGAs at minimum. And this requirement is just because otherwise, if you have one of the amplifiers off, then you'll in theory need infinite gain adjustment range for both VGAs, which is impossible. So instead we add a constant phase offset so that at least both of the amplifiers are somewhat turned on. And then when this is like, in theory, we only need 14 decibels of adjustment range for this, although in practice, it ends up being like upwards of 20. We also need obviously polyphase input. We need a differential IQ input. We need to account for phase variation with gain in the VGAs. So this is not a desired phase shift. This is a bad phase shift that we want to avoid, where adjusting the gain of the VGA causes some phase variation at the output. And then, of course, we need strong phase and amplitude balance from the balance or transformer themselves so that we have a perfect polyphase input to the phase shifter. So this is the actual phase rotator circuit itself. it's pretty simple. It's essentially just, like I mentioned, VGAs with a common source input, and then you have a common gate cascode, and you have two of them for each CS stage so that you can invert the output and achieve a 180-degree phase shift. So you can realize this like negative axis here on the phase plot. Yeah. So like I mentioned, these bias FETs M1 and M14, they form a current mirror with the CS stage, and this is what allows us to tune the gain. We bias the input CS stages at the maximum FT, and then these just detune it from there, which realizes the gain change. And then yeah, LM is just to do some gain peaking with the capacitor, the parasitic capacitors in the transistors, and then LC is just some common mode rejection, and the capacitors are for stability. Yeah, I think that's
do you mind going back to the block diagram? I just want to see where the phase shifter is. Now go to previous one. Yeah, here. So where's the phase shifter here? Oh, those two elements. So you have two phase shifters. Okay.
Yeah.
All right. Okay.
Yeah. So another requirement, like because of where it is in the architecture, is like decent noise performance. But I didn't come up with a strict number for that, so I'll get into that in a minute. This is very slow. Yeah, okay, so here's the actual like realized circuit in XGEM. So in terms of sizing, I went with pretty small MOSFETs. Just like some heuristics about the design, you want the number of fingers on the CS stages to be pretty small, and then you want the number of fingers on the CG stages to also be pretty small. But in general, you just want some decently large FETs. Yeah, this is it. I also simulated with a Q factor of 10 for the inductors, which I thought would be reasonably accurate, but it honestly didn't have a big effect on my design. I even simulated it without the drain inductors between the CS and CG stages and was getting decent performance. It just was like around 3 decibels less of gain, which I'll also get into in a second. So yeah, in terms of performance, these 3 plots are probably the most important, and then my test bench is here. So yeah, we get around an 80-degree phase shift per VGA per common gate stage. So that's a realized phase shift of 320 degrees. And then across the whole phase shift circle, we get a gain of around -6 decibels, and then the noise figure is around 11 decibels. Yeah, the tuning range, like I said, minimum 14 decibels, but we are able to realize 35 decibels here. The power consumption is a little bit high at 25.2 milliwatts, but in some instances, I was able to actually get it down to 600 microwatts. The only problem is the gain then was around -10 decibels, which was a trade-off that I really didn't want to make, considering that our mixers are like around 0 to 1 decibels of gain right now. So
okay. Now I have another question. So at the beginning, I think Max mentioned that you want to have each individual block operating on its own, and then you can do wire bonding to connect those. Is that why you're designing input matching for 50 ohm?
yeah.
Okay, so almost every block is 50 ohm then.
Yeah.
Okay. So
ideally.
I think 25 milliwatt is reasonable for input output matching of 50 ohm. I don't think you're going to have any other choice. But go ahead.
Okay.
Yeah.
Okay. Yeah. The only other thing is on different corners of the process, the only thing that was really changing was the gain. The phase shift and the phase plot was identical. And in these instances, we were getting between like -10 and up to -1 decibels of gain or attenuation, however you want to say it. So the other factor is like we need these balance and like we need a way to generate these phases to drive this. So on the output, we're going to use a balun with center taps because it needs to be center tapped to actually supply the VGAs with power. And then on the input, we're going to use a polyphase filter, a polyphase all-pass filter to generate the 4 phases. And these are just like ideal components, ideal passives right now. So one thing I'm going to work on is actually making this with PDK components, but I haven't gotten to that point yet. And then here's a synthesized balun that I haven't been able to simulate yet, but that's another thing I'm going to work on probably within the next week, is getting this to simulate in like an EMX type of thing, but open source. So I'll be able to characterize that as well.
Okay.
So yeah, in terms of moving forward, I just want to characterize linearity more. I was able to actually set up how to do it, but it won't converge. So I need to like just make some minor changes. I want to keep drive stability as well. Try to improve the power consumption, but as you mentioned, like with input matching, I'm not sure if it'll get much better. And then, yeah, simulate these layouts like I mentioned, and then start layout and do an EM extraction of everything. And one common theme that you'll see in the rest of everyone else's blocks are we have to use MOS caps instead of MIM caps because we have no MIM caps on our process. So that's one hurdle. I haven't reached that hurdle yet, thankfully. So I'm still living in my ideal world right now.
Okay. I think just keep them at the input because they're gonna if you use them at the output when the power is high, then you will have linearity problems. So as long as they're at the input, I think you're fine.
Okay, that's good to know. Yeah. Yeah, I think right now they're only at the input, and then I have some on the, where is it, like the sine voltages to actually invert the output right here for stability, but these are
Okay.
like really small and they honestly don't matter too much. These could be off chip as well, so that's not a big deal.
Okay.
So yeah, thank you. On any other questions? No? Okay. Arthur.
Hello, I'll be talking about the mixers that I designed for this tape out. So as you can see here, this is the block diagram that was shown by Max before. We have two main mixers, one up conversion mixer, which will take an output from the DAC and feed that into the phase shifter. As shown before, the phase shifter's input needs to be differential as it goes into the all-pass filter. So we need to make sure that its output is differential. And we also need to make sure that it's, oh yeah, I have it backwards on the slide. Sorry. The up conversion. Oh yeah, it needs to have a differential output. It needs to have a roughly 2 gigahertz RF bandwidth, so we can work at an output frequency of 22 to 24 gigahertz. And then for the down conversion that's coming out of the LNA, we want to make sure that we're still getting some sort of positive conversion gain to justify the fact that it's an active mixer, and make sure that we're, because our LNA is does not have the most gain as it in theory it could have. So if we can help that with the mixer, we're going to do that. Additionally, we also want to shoot for a lowish noise figure, and also we need a single-ended output, not differential output, that will go into the ADC and take a single-ended input from the phase rotator. Sorry, it's mixed up on the slide. So for the up conversion mixer, something else you want to do is make it a single sideband mixer or an image reject mixer. In this case, because we're up converting, it's better to call it a single sideband mixer, I think. Where what you do is you introduce a phase shift on both the either the IF or RF port, one of those two, and you also introduce a 90-degree phase shift on the LO port. And when you do the power combination on the output, the phase components of one of either the upper or lower sideband can cancel out. And the reason we want to do this is because we still want to have only a single tone on the output of our FMCW radar. However, if we just had a single cosine wave going into our mixer, we'd end up with two tones, and as we sweep the frequency, they'd start spreading up further apart, giving us an image that we want to get rid of. So that's why we're doing this on the up conversion. This is what it is realized. For context, we're using open source tools for all of this. Ryan did all of his work in a software called XSchem, which is and this is a software called Qux or Qux, which is why you might see schematics to look different across multiple people. So over here, it's literally just four Gilbert cells, basically two double balanced mixers where they share the same impedance stage or the same inductors, and that gives us that will allow us to basically get the power combination for free without having to design some sort of Wilkinson power combiner or something like that. Additionally, we have four inputs that are 90 degrees out of phase, which will be given by our DACs, which will be able to give two differential outputs that will be 90 degrees out of phase from each other. And the IFs will also be, LOs will also be 90 degrees out of phase, which can be given by the PLO and VCO, which will be explained later. And it's currently designed to cancel out the lower sideband. So if with our LO of 22 gigahertz, if we give in a 1 gigahertz IF, that will give us an RF of 23 gigahertz. So this is what the performance looks like. It's able to get pretty good power gain of around like 11 decibels up until about 2 gigahertz, which is within our requirements. Its power draw is around 15.12 milliwatts. I was not able to fully measure the characterize the linearity, although I do believe the IIP3 would be on the order of like between 0 and 10 dBm on the input side, and power compression is also similarly between 0 and 10 dBm from what I was seeing. The thing about our open source stack up is that we do not have access to harmonic balance simulations or like periodic steady state noise analysis or anything like that. So all of this has to be done basically in transient analysis and just spice noise analysis, which makes design of this very hard and very time consuming to iterate through because you have to set up sweeps that take a lot
Right.
longer to converge.
Right.
But as you can see on the, sorry?
Arthur, can you go back? And I didn't understand how you combine those. So you mentioned that you have some sort of impedance stage. Can you point out what are you talking about?
So this here are two inductors that are shared for both mixers. So I didn't want to have the wires going around. So this is the RFP, like the positive end of the RF port. It's connected to this node, and this node.
Oh, okay.
That's all it is. Yeah.
Oh, okay. All right.
I thought it would be cleaner to show it this way rather than having a bunch of wires crossing over. Yeah. Any other questions?
No.
All right. And as you can see on the output spectrum, it does fairly clearly cancel out the lower sideband and give very good LO rejection. Now for the down conversion mixer, this one's a little more, this is a little different because we're trying to make it work with single-ended inputs and outputs. And this was also, we're also trying to minimize the use of transformers on this tape outs, just because if it wasn't for Ryan, we were assuming that we weren't able to use transformers at all, and it's a big modeling headache. So we're trying to avoid it as much as possible, which is why we went for a single balance mixer, which can take a single-ended input. The issue of LO feed through in a single balance Gilbert cell is not a big issue because our LO and IF are going to be so different in frequency. So a very reasonable output filter off chip can get rid of our LO almost completely. And then instead of having a differential output, we can use a current mirror as the transimpedance stage, giving us a single-ended output. This then feeds into an output buffer which is matched at 1 gigahertz and is fed which is then fed into the output filter and drives our load. The power draw without the buffer was around a little under 5 milliwatts, but the buffer itself was drawing a lot of power, causing the whole system to have around almost 40 milliwatts of power draw with that output buffer. Oh, sorry. Similarly, linearity I didn't have time to measure that. But I would also guess it would be from what I was seeing, it's on the order of -10 to 0 dBm on the input side for the IIP3. Our gain is we have positive conversion gain over a frequency range of 2 gigahertz, which meets our requirements. And if we're just operating in this range, which is likely based off of what our DAC specs will likely be, we will be having, while the conversion gain will be changing with frequency, it's something we can count for after the fact with software. Some future work with this is characterize the noise and linearity more accurately. While the noise figure I got was 9.6 decibels, and it was roughly like 8 decibels across our range of interest, which was pretty good. I'm a little skeptical about this number though, because I did this using a noise simulation rather than an S parameter simulation like everyone else in the team, because we had to account for the fact we have noise in both the RF and RF band and the IF band and how the noise mixes together. I'm not sure how accurate ngSpice's noise simulation is and how it accounts for different frequencies, so I'll need to do some more digging to see how accurate this number actually is. And then the output stage, the output buffer, that needs to, I think I can improve its power draw a lot. And I believe something about how I designed it is causing this zero in the gain plot, which ideally we'd like to minimize. But those are the two mixers we've designed. Any questions?
No, no, go ahead.
I'll hand it over to Max and Grant to talk about the PLL.
So I'll give a brief introduction on this, and then Grant will take it away with VCOs, and then I'll talk about all the other blocks. So for the IHP tapeout and the RF front end, RF front end, we're implementing an integer n PLL architecture with a lower frequency VCO and a frequency multiplier. The reason we're doing this is that after conversation with Sutton Hawthorne and some testing of like EM simulations of passives, making VCOs work well and making dividers work well at 24 gigahertz is a lot more challenging than making a VCO at 12 or 6. So for this design, we settled on an IQ multiplier. And so starting from there, I'll let Grant take it away and talk about VCOs.
Yeah. So the VCO for our PLL has to, I don't know if it was mentioned before, but our specification is to have 4 gigahertz of bandwidth at 24, centered at 24 gigahertz. So I decided to go with, and we also need IQ outputs for Arthur's mixer, as we kind of mentioned earlier. And the maximum operating frequency of the divider that Max worked on came out to about 20 gigahertz. So we need the VCO to operate at some lower frequency than that, so we get good division. We want an output buffer, obviously, to not unnecessarily load the VCO, and then kind of minimize power consumption, phase noise, and any inductive peaking that could damage the transistors. So I decided to go with a complementary LC. Because at 24 gigahertz, the divider, CML divider didn't work particularly well. And at 12 gigahertz, I was having trouble getting the tuning range with the passives that we had and like the available VeraCap model. But at 6 gigahertz, I was able to get about 1.4 gigahertz of tuning range, which I'll get into later, which definitely meets our specification for more than 4 gigahertz at the operating frequency. And then to prevent the kind of inductive peaking and to help with power consumption, utilize the phase noise as well, utilizing a PMOS and NMOS cross-coupled pair. So that kind of helps to reduce phase noise and power consumption and prevents the need for like a center tapped inductor that kind of causes peaking and could damage the low voltage models that we're using. Also, there are kind of 2 VCOs that are injection locked. This provides our IQ output for the mixer. And then we have, for my output buffer, I used a super source follower. Main goal of this is to reduce the swing, just to kind of get it into a more manageable level. Lower output impedance and kind of isolates the VCO from the circuits that it's driving. So here's the schematic. I have some variables for the sizing, but we're driving it with 1.2 volts. The inductor is that spice kind of symbol there, which is a real model that I simulated in our open source EMX tools. So that is like a spice netlist fitted model of like an actual passive that we have. And then you can see the 2 cross-coupled pairs and then the injection locked MOSFETs kind of that couple the 2 make them 90 degrees offset. And then this is the buffer topology. This one I mostly just took from a paper that I found online, did some optimization of the timing or of the sizing, and this like sizing configuration seemed to give me the least attenuation and provides good isolation between the VCO and the rest of the circuit, or the kind of the loading, whatever the VCO is driving. And here's some.
Can you, sorry, can you
Yes.
go back? So where is the input that for your super source follower? Oh, okay.
Yeah.
So input.
Yeah, so it's taking the V out like positive int or V out P int. That's like in phase positive, like intermediate. That is going into the
So you
V
have
in,
two of these then? You have two super source follower?
4 total. So one
Four
for
total. Oh, okay.
yeah,
Right,
for-
right.
yeah.
Okay.
So yeah, 4 of these, and then those will drive the mixer, or those will drive the multiplier, go into a multiplier circuit and the divider circuit, or at least some of them will. And then simulated on all 4 corners, but these are the typical results. So came out to tunable range between 5.2 or 5.3-ish and 6.7 gigahertz, centered at pretty close to 6 gigahertz. The buffer swing came out to about 650 millivolts. The actual tunability kind of saturates above like 2.2 volts, but it kind of provides some leeway with, so we don't really have, so kind of eases the requirements on the charge pump to not have to like kind of go rail to rail. And we still have some extra bandwidth, so we could kind of play around with what voltages our charge pump's able to reach. Current draw, 23.3 milliamps, which comes out to a little under 28 milliwatts. I believe I have it in just current draw because previous design had I think I had like more complicated inductor like transformers because there's some confusion over what we can achieve with the charge pump. So I was having to be kind of creative with how to achieve the tunable range. So I'm still using the metric that I was using there because it was hard to characterize how much voltage was traveling through or the voltage drop across the transformer. But yeah, it comes out with this one, it comes out to a little under 28 milliwatts. And then with the phase difference between the IQ or like the in phase and quadrature phase comes out to slightly below 90 degrees, which should be good enough for Arthur's mixer to kind of achieve what he needs to achieve. And then also some phase noise. I know the plot's kind of not exactly tuned correctly, but with or like scaled properly, but there's some convergence issues with reducing the bandwidth of the simulation kind of messes up the convergence. But the maximum phase noise is from about 800,000 or 0.8 megahertz to 94 megahertz, and that value is like the 1.71 times 10 to the negative 10 or times 10 to the negative 5 dBc per hertz. And then that one's just, the other plot here is just like a output of I believe that's of the buffer
Yeah.
output.
So for your phase noise plot, you want to just focus on maybe the first 100 megahertz or 10 megahertz. So you don't really care about the frequencies that are far away.
Okay. Thank you. Yeah.
Go ahead.
Yeah. I wasn't not too familiar with phase noise, so good feedback.
Yeah. So it's, like you're oscillating at, I don't know, 6 gigahertz. If it hops around, say, sometimes it's 6.1, sometimes it's 5.9, you want to see the energy of possibilities of 5.9, 6.1, right? So you go away from 6 gigahertz, and the farther it's reduced, let's say it's down by, I don't know, 80 dB, and the less phase noise you will have. That means your signal is more pure, right? So that's really the concept. So that's why you want to see it around, maybe 10 megahertz, 100 megahertz of the carrier signal.
Okay.
I don't know what it means, so you have something at 10 gigahertz. I don't know what that means, because the chances of this hopping to 10 gigahertz away from 6 gigahertz should be very low.
Okay. I'll have to look
So
more
I
into
think
that.
that's some sort of artifact.
Okay. Yeah, thank you. I'll have to look more into that and
Okay.
explore the phase noise. I think,
It's me.
yeah,
Yes.
pass it off to Max.
Lovely. So with the PLL, I have been working on the divider, the phase frequency detector, and the charge pump. Most of my time has been spent on the divider though, so I'll start here. With our topology, we have a limited bandwidth of our RF DAC, right, and ADC, right? So in order to be able to sweep a wider kind of like overall bandwidth, we wanted a PLL that was able to tune its output and adjust our LO from 22 to 20 to 26 gigahertz. Grant touched on this with the VCO, but from my perspective with the divider, I'm receiving a sine wave between 5.5 and 6.5 gigahertz, right? And I need to divide it first down to a workable digital speed, and then I believe it's between like 60 and 88 times. Like divide by 68 to divide by 88, so that I can get the range of frequencies that allows us to set the PLL exactly where we want it. The way I'm accomplishing this is with a very standard integer n divider using a pulse swallow topology. So in this diagram that I kind of show here, first off, I divided it down using a CML divider because the limit of our digital circuit, like a DFF, will switch around 4 to 5 gigahertz, but it wasn't stable with a 2 DFF divider at 5.5, or at least I wasn't seeing the stability I wanted on slower corners. I then buffered that signal to turn it into something closer to a 50% duty cycle CMOS signal that then drives a TSPC, which is true single phase clock prescaler. I'll talk about all these blocks in a little more detail, but effectively what's getting produced here, right? Out of our buffer, we're really getting this frequency in symbol here, right? Output of what's labeled CAP here from a paper I've been using as a reference is actually the output of the TSPC prescaler. So that has an input called modulus control. When that is low, right, for example, here, you can see how this alternates every 2 clock cycles, right, divides by 2. What's that? The microphone. Okay, yeah, good point, good point. You can see my cursor though? Okay, yeah. Like here, you can see how it's dividing by 2, right? And when modulus control goes high, it's now dividing by 3. The reason this is useful is you can kind of achieve like any integer division ratio using this equation, where it's 2 times the number of cycles that it divides by 2, right? Which is going to be the kind of total count window, right? Like I'm waiting for n counts or m counts out of C out, minus s, which is basically the number of counts until it switches to a divide by 3. So it'll divide by 2 for some cycles, and it'll divide by 3 for some cycles. Those will always equal the same amount in this topology. In my case, to keep it simple, I tuned this so that it always divides by 32. It always takes 32 counts, right? Per like output clock cycle. That being said, it takes between 5 and 17 divide by 2s before switching to divide by 3. Very rushed explanation, but that's the overall concept. And so I'll go into all these blocks a little bit more, but what's missing currently from this design, so we don't get the end instead, is the swallow logic is too complex to do by hand, realistically. And I need to write it in HDL and synthesize that because it's just a large combinational block. It shouldn't be challenging, so to speak. That being said, I do need to not do that by hand because that would be very unpleasant. Getting to our CML stuff. So CML is, as far as I understand, the fastest way to do logic operations in CMOS processes at the expense of higher power and non-square wave outputs that are a little harder to deal with. So from our VCO, we get a sine wave out of that super source follower that Grant talked about. And it goes into a CML divided by 2, which exists using 2 latches. One of these latches is shown over here. And you can kind of see there's like an M1 and an M2 and an M3 and an M4, right? And what those are doing is depending on the phase of the clock. So it's a differential in, differential out topology. Depending on the phase of the clock, if the clock is high, M1 and M2 will track the signal basically. When the clock goes low, M3 and M4 fix it where it stays, right? With like that positive feedback in that latch. By using 2 of these, we can actually achieve a divide by 2 circuit. It's kind of hard to follow here because of the labels to make it not like a rat's nest. That being said, your inputs would be this clock N and clock P, right? And your outputs would be QN and QP, though it is symmetrical, right? So you could also get outputs from in N and P. Like fundamentally, it takes in a clock input, right? And by steering current between those 4 resistors, right, you basically get a differential sine wave voltage output. In terms of results that I've been getting from this, given like a worst case VCO input, right, of 200 millivolts input swing, with my slow corner and a slightly reduced input voltage to account for like loss in our like power lines inside of the chip, I'm getting 470 millivolts of output swing and very good stability. This specific divider was originally designed to be operated at 7 gigahertz, which helps get good performance when we run it at 6.5 or 5.5. In general, my W over Ls are pretty reasonable. 46 for all of those switching components, and you actually do want these 2 FETs to be sized the same, because you really want all the current. So you want current to either flow through this and this, or that bit there and this one, to maximize kind of the difference in current through those resistors, which improves your peak-to-peak output. This is relatively done, I would say. And so in order to take this and move it to a TSPC stage, which is a lot more sensitive to input swing and also input duty cycle, I'm using a self-biased inverter. I'm actually using 2 of them, but I said just show for 1. And the idea here is that we're basically just using effectively a CMOS inverter with that resistor that, as far as I understand, improves stability at the expense of some gain. But I'm doing like AC coupling into a buffer, and then it spits out effectively a CMOS signal to my TSPC. To be honest, if you asked me questions about this, I would have a hard time answering them because I pulled this from a paper and it worked fantastically. That being said, I have some due diligence to do on a circuit that will happen. But the benefit of this is it takes that 3.25 to 2.75 gigahertz output of the CML divider and turns it into a fairly usable like CMOS square wave for the TSPC. Also, the CML divided by 2 consumes 1.12 milliwatts, which is reasonably acceptable. I've seen literature that does better on slightly different nodes. But I'd rather tune this for stability because this is a long chain. And if anything fails in this chain, then our PLL is shot. And so I will take the like 0.12 milliwatts of power increase over like reducing my stability and confidence in the circuit. This is relatively low power as well. So in terms of the TSPC prescaling, this circuit is operating effectively like a normal static CMOS 2 or 3 divider. However, it's all implemented using this true single-phase clock technology. The idea with this tech is that under certain conditions, your nodes are not actively driven high or low, and instead they're floating in between 2 MOSFETs that are both off. The benefit of this is that your signal propagation isn't limited by the speed of your MOSFETs turning on and off, and it can propagate forwards just by being held in the drain source and gate drain capacitances. The downside of this topology is it's sensitive to leakage and actually won't work at low frequencies. So it wasn't viable to implement using flip-flops, right? And TSPC provided the right balance of speed and power that could not be achieved with CML or static CMOS. After kind of hashing out the whole topology and choosing like the correct combination of elements, and I didn't include the circuit because it is like a lot of transistors. It is pretty much exactly this. My W over L for all of this was relatively the same. That being said, the PMOS's W over L is increased a little bit to account for the fact that PMOS's in my testing were less leaky and also less conductive, or less transconductive than an NMOS. All the lengths are at minimum. And if I was using this at a lower frequency, the length would be increased. And also there are some other topologies that deal better with leakage, but this was the fastest topology I tested. And I didn't have an issue up to 3.4 gigahertz at a lower VDD. So with all of that, I do need to take it and do parasitic extraction for my layout, but fingers crossed, with some tuning, it should be a functional topology for this. So as I kind of mentioned, I don't have the master and swallow dividers done yet. That should be straightforward with like synthesis, but I did not get around to that yet, and we're still kind of finalizing those workflows. So I decided that it was a better use of my time to push forward on stuff like the PFD and charge pump instead of just trying to handle that. Yeah.
I guess just one question.
Yeah.
So what is the input frequency to your, I guess, to those, to counters and things like that after you go through the prescaler? Is it
From the
around 1
prescaler,
gigahertz?
It's 1.2 to 1.6.
Okay.
Which, sorry, go on.
And so you want that to be okay. 1.2 should be okay. I'm a little bit concerned that, I don't know these technologies, so I don't know how fast the digital implementation would work. You do want to worry about it a little bit. Don't leave it for the last minute.
Yeah, no, absolutely. We have a little bit of information on, or I should say, scratch that. We have very little info on gate delays in this topology. But the divide by 32, basically like that, like master counter, I have characterized up to speed. That being said, I didn't think it was worth putting that in. It's just D flip-flops in a row. But at the like 1.6 gigahertz even, I did find that to be stable. And the D flip-flop challenge, then the reason I didn't want to use it for, like, it was non-viable at the CML speeds. At the TSPC speeds, it didn't work well because you need to have like 2 D flip-flops with additional combinational logic. That being said, the individual D flip-flop like divider, I can say pretty confidently will work at those speeds. That being said, it definitely needs to be addressed, and I'm pushing forward to at least like do a master divider and then maybe like input like a Verilog block into ngSpice to like pretend it's the combinational logic just for like closing the loop and testing while we finish that block. Because the PLL fun starts once all the blocks are done, realistically. So looking at the phase frequency detector, our actual phase detector frequency is 40 megahertz from an external crystal oscillator that'll have a 3.3 volt CMOS input to the chip. Because of how low this frequency is, I decided that it was reasonable to use like a basic PFD like shown in Rosati. And I implemented this all with like high voltage min size FETs. I didn't want to just synthesize this digitally because we don't have accurate analog models for the digital blocks, which was a concern for this circuit that cares more about matching. And also like the layout matters a lot on this. I was able to confirm the performance of the PFD. You can see kind of the expected plot of a PFD, where as the phase difference gets larger and larger, right? You don't just have like continuous it doesn't repeat every 360 degrees. If it continued on further, you'd see the same kind of sawtooth waves of average output A minus average output B. And then it kind of on a more like finite scale on the right, the center image is a locked loop with 0 phase offset. The top image is a leading scenario with a 90-degree offset, and the bottom image is a lagging scenario. I do still have more characterization to do on this in terms of dead zone, running more corners, making sure my matching stays okay in like slow, fast, fast, slow. But at 40 megahertz, speed's not a concern, and this should get adequate performance. Slash, we'll find out if it does when we go into loop stability analysis. And then for the charge pump, the goal of this was to be wide swing from ideally 0.2 to 3.1 volts. As Grant showed, the VCO doesn't really respond significantly above about 2.5 volts. So the upper end is less of an issue, which I will tune my design for the charge pump in the future. Relatively, until we start closing loop and adjusting the poles and zeros on our loop filter, the specs on this are variable. I needed a working basic topology that was easy to tune so that when we go to close loop and do stability analysis, this can be adjusted. And I haven't put as much time to this as I did into the divider. So a lot of the work into this was just like creating like finding the right topology, putting it down, choosing like reasonable biases, right? And then basic characterization here, where you can see effectively the like V out of a example charge pump, basically, from different starting voltages. Or sorry, the V out across an arbitrary loop filter at different starting voltages. So it is reasonably linear until it gets down to about half a volt or up to like 2.8 volts. And I'm going to try and work on the wide swingness on the NMOS side using some techniques from 4656 perhaps. But no, this was the last thing I was working on and needs a lot more characterization still. Do you have any questions on those two? And then I can talk about next steps and.
No, go ahead.
Yeah, okay. So the PLL still needs a lot of work, clearly. Fundamentally, the divider chain is the first thing that should get addressed, right? With like a temporary Verilog block, and then also working to just like verify timing on that on the RTL and like synthesize that / lay that out. Between the divider and the PFD, I'm going to implement a level shifter, which again should be simple enough that it's not a concern. But on the PFD, from what I read, you want both inputs to be matched fairly closely, right? You want like similar slew rates, similar behavior of those inputs to make sure that it's stable in its performance. So that was definitely not a concern, but that was something I took into account with making both sides 3.3 volts instead of having like one side of the phase frequency detector be 3.3. Digress. We need a level shifter. That's straightforward. Grant could talk briefly on the frequency multiplier. You have a topology.
Yes.
And it is tested. The challenge we're seeing more is amplification between stages, or
Yeah, that's
yeah.
The next steps for me is just making or designing a frequency multiplier. My current plan is to do a differential in, single-ended out to get from 6 to 12, and then from 12 to 24 single-ended in, differential out. And then there'll be a buffer stage in between that provides amplification because the actual multiplication attenuates the signal pretty bad. So that's just for the frequency multiplier. And then I did have, I guess once we're done, I have a quick question about phase noise.
And then the only other thing with PLL is loop filter and loop stability. This is something that is hard to simulate in Cadence and very hard to simulate in open source tools. And so I'm planning on reaching out again to Sutton Hawthorne. Grant and I reached out to him in the past, and he kind of gave us some good insight early on in this design process. And I imagine he would have pretty good insight in terms of both what to simulate and what metrics to shoot for in a design that'll actually be taped out and not just be kind of done in simulation. Any questions? Thoughts?
Okay. Actually, are you guys finished, or there is more presentation?
There is more.
Okay.
Yeah,
Well, let's go and I'll
sounds good.
Yeah.
Reinforcement was quite a lot better.
Do we want to do LNA?
Yeah, can we skip that one?
Yeah,
Or power PA, because Alec is, I think.
I see. I'm gonna skip ADC for the time being. And then
Unless you want to do LNA first, to you, Alec.
we can go.
I'll get it, yeah. Okay.
All right, take it away.
Hey, Professor,
Okay.
I was working on the power amplifier. So for our application, we were thinking because we're doing a radar SDR sort of thing, there's quite a few opportunities when it comes to applications like integrated communications and sensing and things like that. And so my task was basically to find a PA topology that would kind of fulfill a balance between linearity and efficiency. I don't know if you recognize these pictures, but there's a few common PA topologies out there. The first one I thought of when it comes to efficiency is a Class E architecture. Obviously, theoretically, it has 100% efficiency, but the two problems I thought of the two problems that led me away from it was the fact that for one, the F max of our node is about 110 gigahertz. And so we'd be operating on like a quarter of F max, which might lend itself not very well to like switching applications, as well as the fact that it's not as linear, and we kind of need linearity for our waveforms. Another architecture I considered was a parallel current combining architecture, but because the elements are in parallel, it means that you need a higher impedance transformation ratio to get your optimal output impedance. Versus for the stacked architecture, the optimal impedances add up as you go up the stack, so you can more easily match the 50 ohms. So I decided to go with a stacked architecture. So on the left there is a picture of the circuit that I currently have. I'm going with a 3 stack. From what I simulated, it allowed me to get the closest to 50 ohms, and I wanted to make sure that the matching transformation was as small as possible. Now, one issue that I ended up having was basically trying to find the optimal capacitance to put on the gates of the top and the middle transistor. What I basically found was that it was very difficult to get a high gain amplifier that was not oscillating. I have an example in here of the PA that I have that doesn't oscillate. It has a gain of like 4 dB. I did have other PA topologies or like versions of this that did meet our specs, but they were oscillating. Now, the main reason is that the capacitance of the transistors is very, very low. I guess that less to do with oscillating, but I did want to get your opinion on this as well, because when I simulated the capacitance of the transistor, it was only about 80 femtofarads. And typically the capacitor you put on the gate is usually a little bit less than that. So I was kind of running into some concerns with like the gate capacitance and stability with the PA. But on the right there, you can see that for the one that I have on here, I was able to get good phase synchronization between the waveforms at the different nodes. Although because the capacitors I chose are a little bit larger here, it operates more like a cascode than a traditional stacked PA. Something else to keep in mind with this, as Arthur mentioned, is that the tools that we have are unlike Cadence in that basically every tool I need to simulate this is not actually in the tools that we have. So I had to code my own like load pull simulator, my own on the plot there, I had to code that myself. But you can see there, based on the results that I have right now, I'm able to get a gain of about 4 dB and a PAE of about 25%, which obviously is not within our specs. But I was wondering, do you have any thoughts on just ways to size the capacitors that you put on the gates of the top 2 transistors? Because I was struggling with maintaining, like having it not oscillate.
Yeah, Alec, my main concern is breakdown, because first of all, this stacking can be easily done on SOI processes, not necessarily on bulk CMOS. Is this technology SOI or bulk CMOS?
We have triple wells in
You have
the
triple wells.
technology,
Okay.
so we can connect the body to the source.
Okay.
Is that the advantage that you were thinking of with SOI?
Yeah, yeah. Still, you want it, maybe the best is just look at the transient and look at all the waveforms, make sure drain to gate and drain to source voltage for each transistor does not violate the breakdown. There
Sure,
should be
yeah.
some numbers for the breakdown voltage. So
Yeah, the breakdown, I tried to bias the VDS, at least the DC, at about half of the breakdown.
okay.
Yeah.
All right. So in terms of choosing the values and stuff like that, I think everything you do now, you will probably have to redo it when you go to layout. So,
Sure.
and then for oscillation, essentially oscillation happens because you have like positive feedback. And the reason for positive feedback is that you have some of the signal going from, I guess, drain to gate. Gate cannot be grounded because you want equal signals and stuff across the VDSs. This may be a little bit challenging. My suggestion would be maybe it's easier to start with a cascode, just 2 transistors. How much power do you need to deliver?
We kind of ballparked it at 0 dBm. But that was a low estimate. You could use a cascode for that, certainly.
Yeah, yeah.
But
And you could do like differential PA. Can you do like does your antenna have to be single-ended, or can you actually go
we
with
could
a
have some sort
differential?
of like Balun off chip or something to combine.
Um,
Or
yeah,
like
but that will
rat
have
race coupler.
loss. Yeah, yeah, okay. But 0 dBm should not be very hard to do.
Sure, yeah.
So
Although
I
like
would just go with a cascode, try to make it efficient, and it's much easier to deal with rather than this. This
that's
is,
fair.
yeah. And you still have like why your gain is so low anyways?
So I chose this one because it was one of the topologies I had that didn't oscillate. For ones that had a higher gain, it would typically be oscillating. So like I definitely have higher gain options. It just I didn't want to put one on here that was oscillating because it wouldn't be a valid result.
Okay, okay, yeah, understandable. Well, I guess your efficiency is limited by this low gain anyways, so that's why
Yeah.
you're okay. All right, go ahead. No, I mean, I have some general comments for all of you, but I'll wait until the end, so go ahead.
Sure. You can do LNA now.
Okay, let's go. So I'm on the LNA, so very quickly, I think we finally decided on a bandwidth. Originally, I was told to do 20 to 26, but we're now officially 22 to 26, so just assume for this presentation, the bandwidth is just 21 to 25. I will adjust it later tonight, now that we're locked in on the PLL. So bandwidth of 4 gigahertz, of course, I need the LNA to have a noise figure of less than 5 dB. I need it to be unconditionally stable and, of course, minimize the power used. I also have S21 at 20 gigahertz to 26 gigahertz, are about 20 dB, and this is just to help Ryan's phase shifter that does not have positive gain. Next, the topology used is a cascode with resistive feedback and inductive load. I've used 3 stages of this, and I have a T-match for low noise figure. The reason I don't have inductive degeneration on the bottom is I found that as I increased the inductor, I had the gate inductor and the source inductor. I found that I wasn't able to match to 50 ohms, and also it seemed to increase my noise figure and decrease my gain. So I removed it because that's the trade-off we're looking for in an LNA. And of course, the reason the LNA is important for everyone else in the room is the noise figure of your whole system is dictated by the first noise figure, which is from the LNA, and the gain, because the noise figure of the second device, which should be the phase shifter, will be divided by the gain of the low noise amplifier. So
here's just my schematic overall. You can see 3 stages of resistive feedback, and you can see a T-match, which I will take off chip. The thing that y'all might say was, how are you going to get a 67 femtofarad capacitor off chip? Well, I looked at DigiKey, and they offer 0.07 picofarad capacitors, so we can take it off chip.
That's capacitor. How are you gonna get one that has a it's gonna work at that frequency?
We'll think about that later, but good point, actually.
It's a more
Yeah.
capacitor.
I can reduce that to like, I think 1 nanofarad if possible. So for the next portion, for noise figure, using the T-match, I was able to optimize it to match almost perfectly to the NF-min. And as you can see, I'm below 5 dB across the bandwidth that I guess I personally chose for this. And then for S21 in the bandwidth, I have a max of center frequency at 23.39 gigahertz at 24.88 dB. Then I have the low frequency and the high frequency. This comes out to a bandwidth of about 4.65 gigahertz. And that's, we'll take extra bandwidth, so I'm not upset about that. And of course, my S21 at 20 and 26 gigahertz has a gain of 20 dB. And then finally for stability, I'm just going to gloss through these slides, but so I found out in Clux, there is a stability feature. If you use the line matching tool to try and match your device to 50 ohms, it will tell you when you're unstable, but there's no hard-coded feature to do stability. So I use the Nutmeg equations tab to get delta, which is beta, then mu, which is, it's called beta and delta depending on the book you read. I guess I chose beta. Then mu, k, and mu prime. So for stage 1, I've tested each LNA independently of each other for stability. And I'm just going to gloss through these. Everything is above 1, but I want to have them listed just for reference. Stage 3, and then the entire LNA, which is very, very stable. So that's good. And finally, for power draw, I'm drawing about 11.595 milliwatts, which is 9.66 milliamps, which is pretty good. And for future work, I'm looking for ideas, and I'm thinking maybe about using Arthur's buffer. I want to improve the matching of S22 because whenever I try and match S22 to 50 ohms, I lose a lot of the wideband, and I seem to drift more towards the 22 to 26 range, which after this presentation, I think is what we're looking for. Linearity, I need to test also as well. I ran out of time, and then finally just moving to layout. So, yeah, and that will complete the RFIC portion of the design, yeah.
All right.
Any questions for me, of course?
No, I guess not. I guess I have some comments for everyone. One thing is that when you do presentations like this, make sure if you use certain papers or certain books as reference, provide the reference. And the reason for that is, if I had the reference in front of me, I would be able to tell you, let's say, whether this approach is good or not, because there are some papers out there, there's some, methods out there that are not really proven. They're just maybe simulation or something. And sometimes we make that mistake to try to do that and then it doesn't work. So not just for this presentation, for every presentation, I would just make sure I have all the citations, everything that I have used. If you have come up with an idea, so that say it, but if you have, if you were inspired by some, or you changed some design or you copy the design from the textbook, I think I saw 1 or 2, but in general, you want to have that. And then if you don't mind, send those to me. So maybe add those references and then send this presentation to me. There's a lot of material that I need to review and then try to get you maybe give you some feedback, but it's kind of hard to absorb all of that and be able to provide that feedback. For your immediate stage, I think most of you are getting ready to do layout. Before you even start layout, maybe tune your circuits a little bit. If you're designing, let's say, for 20 to 24 or 21 to 25 gigahertz, your schematic should really work around, I would say, 24 to 28 gigahertz, because you will see that shift, all right? So instead of doing it twice, it may be better to just tune it a little bit now, push it to a slightly higher frequency, and then when you do layout, you will see that it slows down. It will come back to the frequency that you're aiming at. Maybe for the 6 gigahertz oscillator, it may not be that very different. So maybe you have to design it at 6.5 or 7 gigahertz, slightly higher than. But yeah, so for the rest of them, I think it's a better idea to do slightly higher frequency in the schematic and then move it to the layout stage and see that effect. I'm not familiar with your open source software, so I really don't know how accurate it is, how good it can catch oscillations. But I would say almost in every block, whether it's power amplifier, LNA, PLL, your frequency divider, almost everything oscillates, okay, the first time. So the more you do to catch those oscillations now, the higher chance of success. So even sacrifice your performance to have, let's say I'm designing an LNA and my, I don't know, K factor or stability factor supposed to be 1, I design it to be 1.1. That's probably very risky, because you want to design it such that it will never oscillate. So design that K factor to be 2 or 2.5. Same thing for PA. Because just you want to get this to work. I think that's the most important part, that everything should work so you can connect them and you can see some system level performance. So keep that in mind, how to improve stability. When we use cadence, we have these test points that we can actually assign inside the circuit. So for instance, for the PA circuit that you have 3 transistors stacked, it may be that your PA is stable, but inside you will have some problem that they will oscillate from inside. The internal nodes, what I mean is internal nodes. So Alec, you have to look at that and make sure that you don't have those kind of problems. Again, I don't know the difference between this software and cadence and the PDKs that we have. For PA, definitely look at the peak to, like signals, make sure you don't get close to the oscillation. If you want, you can go to the very first presentation, and then I can maybe provide a little bit of feedback for each.
I'll go to the exact start, my bad.
Yeah, I would.
Yeah, we can start from LNA. So
okay.
definitely, I mean, move the frequency a little bit to higher frequencies. I think you're getting the target. I think 3-stage cascade is good. How much power you're dissipating here?
11 milliwatts.
And are your stages are identical, or you're changing the design?
Changing width and length to reach wideband at each stage.
Oh, okay. So it's going to be a nightmare for layout, but yeah, at least you don't have a lot of inductors, it seems like.
Yeah.
So that shouldn't be too bad. Okay. We can go to whoever wants to talk about. So let's go to.
I think we should just scroll through the slideshow.
Just like
Sure, okay.
Yeah.
Let's go.
Yeah.
So for phase shifter, okay, I'm not very
that
familiar with this phase rotator concept, but yeah, it seems like a little bit low risk to me, so it's fine. I worry about those balance at the input and output, the transformers. Typically at these frequencies, you're expecting, this is 20 some gigahertz, right? So you expect after you do layout about 3 dB loss or so from each of them. So keep those losses, keep that in perspective that, okay, if I have 3 dB loss at the input, 3 dB loss at the output, what would happen to the overall system? They can be designed better, maybe 1.5 dB loss, but yeah, that again depends on the technology, how thick is your metal and stuff like that. For these transformers, you want to use several layers of metal to reduce the loss. But that also reduces the frequency. So it will be harder to design at 24 gigahertz, something that is higher Q, less loss. Okay, let's go to the next one. Yeah, I like this mixer, and I think that yeah, the challenge would be that you would have to do layout and you would have to do corner simulation to make sure that your I and Q match well. Especially for designs like this, everything has to be very symmetric. So always remember that the two high frequency ones should be coming from the two sides, and then IF, the lower frequency one, can go from up or down. It doesn't matter. But the reason for that is, let's say if you go from east to west, if you have both I and Q and they're supposed to be 90 degree, or even if you have differential, so they're supposed to be 180 degree out of phase, you don't want any bending, or but let's say if RF is coming this way, LO is coming this way, you will have to bend, and then that results in mismatch in the phases. So always try higher frequency signals to be facing each other in a mixer, and IO should come, IF should come from either bottom or top, because that's a lower frequency. All right.
How does that? Never mind. I was gonna
What's
say,
that?
I was gonna ask, how does that affect the Dow conversion mixer? But it doesn't matter because there's two high frequency signals, but it doesn't matter because our RF is every single ended.
Always the high frequency signals are going face to face. All right. For VCO again, I think the design is pretty good. Yeah, has to be I guess you want to oversize your transistors a little bit so that you know that it will oscillate. Okay, so let's say you're running the simulation, you do the schematic, and then in layout maybe choose a little bit larger transistor, because you will have more parasitics, more capacitance, and you need more transconductance to compensate for that. So maybe oversize. It's okay to consume. Again, this is your first design. It's okay that it's not perfect. So spend a little bit more power, make sure it will oscillate. All right. I think the inductor or the balun you're showing here, this one, page 23, is this already, you have already extracted the parasitics for this? So
Yes, this is just a two-turn inductor. This is like the layout model of the inductor that I'm using for my VCO. But
okay,
yes, it's extracted.
okay, so in that case, that frequency shift may be smaller. I don't know. But we see that, and even when we do measurement, we see that whatever we have done in EMX, or it may be unique to global foundries, but usually we see another shift of a few gigahertz compared to EMX even. So yeah, good. Okay, so let's go to the next topic. All right. This I think is very smart. So using CML as the first divider, is very smart. we have had some issues with our divider, and I think take a look at the output of the CML when there is no input, and see what happens. And do you see oscillations or not? And then you may want to talk to, I think Thomas, you guys know Thomas, right? Thomas Greer. No.
Yes. Yes.
Yeah,
No.
so he and Mohab are trying to fix our PLL, right? So maybe it's a good idea to talk to them about what they're doing. But I think you're doing something very similar. Remember that when you're doing layout and you have these signals that are at, say, 6 gigahertz, you know, they are not digital signals. So give them enough space so that they don't couple to each other, and they have to be wide enough so that, so don't minimize the layout dimensions for whenever you have higher frequency signal going through, okay? And that's important for this because you're treating this as digital, right? The output comes, you have to divide it. Don't treat it as digital. These are RF high frequency signals. So the path should be wide enough. Distances should be, you know, path should be 10, 20 micron. Distances should be 10, 20 micron. Something like that, right? So keep that in mind when you're doing layout. And when you go to lower frequencies, of course, then it becomes less of a problem. So hopefully, but maybe the first two dividers, you want to make sure that you're designing them using RF rules, right? Not digital rules. All right. Let's go to the next one.
Is that all
Okay.
the RF blocks, or do you want to talk about more divider stuff? Or I guess PFD,
we have
PFD.
PFD.
I lied.
Yeah. Oh, okay. Yeah, this should work. This, I don't think it's very difficult to get this to work.
Charge.
Oh, charge pump, my bad.
Real quick. Yeah. This is also pretty textbook, relatively.
Yeah.
Yeah. I
Yeah,
think
this should.
yeah. The issue will be when we simulate full loop and make sure it doesn't oscillate instead of block. I guess that's pretty much all of the RF side. I don't want to cut you off if you have more things to say, but
PA.
oh, we didn't go over PA. Oh, you're so right. My bad.
No, PA is not RF. That's
Yeah, PA, yes, digital.
audio frequency. Basically, PC.
Don't worry, it'll load eventually. Okay.
Yeah, so I said that, Alec, you should probably just try a simple cascode. Don't make it too hard because then it will be harder to design. Just the I guess look at maybe if you look at papers and see how the people have published cascode power amplifiers, right? So take a look and see how the layout is done, because that's also very critical.
Sure.
Okay, but 0 dBm should be, you know, you want to aim probably for 5 dBm or something so that you can actually deliver 0 dBm. Okay.
Sounds good. So we went through all the RF blocks. That was a lot of members who either have taken one of your classes or have some prior experience in this. In order to bring newer members into the club and also kind of just like close out this system level design with the digital side, we also have that like RF ADC, which is a lot slower. It's targeting like 600 megahertz out maximum, and then also RF DAC that's 600 megahertz out, and the RF ADC that's targeting 1.2 gigasamples. Recently, we dropped those specifications a little bit because on GF 180, it's not a very fast process. And there were a lot of challenges, but we do have that team here. We don't have our DAC person. She had something come up, a very reasonable excuse. And we're also talking with Professor Swaby about the digital blocks. So the person doing FFT is reviewing that with him. And then our DAC person is doing that as well. We may also send you something once she makes slides.
Sure.
If you can look at the analog
Sure.
part. But for the time being, we're
right.
doing a 8-bit flash ADC at 1.2 gigasample. And we kind of have all the blocks like broken up to different people or different groups.
Mhm.
So we have a little more time. You guys all have slides. Which one of you guys wants to go first? We can talk about that.
Sure.
All right, you guys go first. Cool.
Right. So my power is
the camera's over there. So
Oh, yeah.
So
Gotcha. Yeah, my power is thermometer to binary encoder. So we'll be taking before it was 15 comparators, and it will go into a huge block of a combination of logic, and it will output a 4 bits output. So since it's just a huge chunk of combination of block, I'll just synthesize this by writing Verilog, but for some reason the slack was horrible. The power is net. Power is 2.24 milliwatts, which is fine, but after synthesis, I think just look at D flip-flop alone, it's like 2 nanoseconds slack. So my next step will just be completely steering away from digital design into purely just converting everything to CML. So
you also might be able to, sorry to interrupt you. You might, because of like the way it fans out, with like one single D flip-flop driving like many gates.
oh
Did you
Yeah.
with that?
So when I was synthesizing, I actually by the way, using 4-stage pipeline as well, and I also tells you to insert buffers, also add some timing constraint in the SDC file. So I assume to choose the buffer with, or like the gate with the higher drive strings,
I see.
and yet it's still, yeah.
If you could characterize just an analog domain, like design D flip-flop, and like if you do it yourself in analog domain, what you could potentially do is just like size up the transistors in your static CMOS logic element. So instead of having logic element with propagation delay into a buffer, which then you have the delay of like a large buffer to drive a lot of gates, also has like a large input capacitance, right? So it's going to be slow from like the input to the buffer, and then your buffer will also take time to switch. Doing it where instead of having a buffer, you just size up your actual logic components and hand wrap them is unpleasant because of the amount of analog routing you have to do. But I'd be curious to see if you can characterize those speeds in like an unloaded state. No, I'm sorry to keep interrupting you.
Oh, no, you're good. Yeah,
Sorry, go on.
that's a good point. But yeah, next step would just making the CML for NAND or XOR and latch, and using 3-stage pipeline for the same logic block. And it seems to be doing fine. Right now it's at 1 megahertz, but I think I push it faster, and it has some glitches. It's probably because the rise probably give more rise time. Because it seems like there's charge injection right now. But yeah, that's what I have right now.
So the other part of this is that in the LVDS transmitter. So from the output encoder, this is how we're going to take our data off chip. Oops. So basically with this following the LVDS specification, the input or the input will come from the output encoder to be level shifted up from 0 to 3.3 volts with a square wave. And then our output is listed there as the specifications. So this is the block diagram. On the next page, I'll show our output in the actual way we implemented it. But as of now, we need to add the actual level shifting. And also we have to do the whole integration for each channel, because right now this is just a singular driver. So we have to make basically a top module with all the other components. But with this, we have the input and output or the differential signal. For LVDS, the spec says that logic 1 is considered to be 150 millivolts or higher, and then logic 0 is less than negative 150 millivolts. So we have a lot of headroom with the output. And this was all done in the most ideal simulations, so it's good that we have that much headroom. But then, yes. The last part of this, we also had to make a clock buffer for some of the clock distribution. I didn't implement it in a very ideal way. So I have to fix this. I just thought I'd add it in because for the sake of showing everyone else that this block still has to be fixed. But that's all for our section of the project or our blocks.
Okay. You don't need LVDS receivers.
That's
We're planning on having LVDS be from the GF 180 chip to an FPGA. So the thought is like have like an LVDS block that we can use for any outputs from the chip, for ADC or FFT outputs. Okay.
Sounds good.
Sounds good. Sorry. Sorry, no, already. That's sweet.
This camera?
Yeah, that's the camera.
Okay, hello. Us three are working on the track and hold, and we're making a very, I don't know, well, we're using an input buffer, a switch, then a hold capacitor, and then an output buffer at a very high level. You guys probably already know that. I came up with a 1 gigahertz bandwidth target for myself this morning, right after I ran the simulation and got above that to show that I hit my specs. But in reality, we just need 600 megahertz of bandwidth, so this should be all good. Originally, the original specs had us trying to get over 10 gigahertz, which made it quite a bit more difficult, especially for us who don't have like so much experience in this area. So we copy pasted a research paper that didn't work, and we were in for I don't know. It was a rough couple months, but now we're yeah, it's a little bit better now. So at -3, the bandwidth for 0.1 decibels is above a gigahertz or 1 gigahertz, so that's pretty good. The topology, which Elliot will talk a little bit more about at the end. This was our reference one that we like copy pasted. It works in like some very specific situations. It's kind of, and we're not supposed to like use inductors, so we had to modify it quite a bit. But this is kind of what we based our idea off of, and this is what we originally had. And then once we got the relaxed specifications, we could make it a lot simpler. So what we came up with is a very simple switch design. Just a PMOS, NMOS, drains and sources connected. When V clock is low, it cuts off, and then when V clock is high, it obviously opens up and allows it to track. And then if you want to look later, but this is all of the like the inputs that were used in our topology, which we'll get to later. This is what I was showing people yesterday, because I was quite happy with the result output. But what they didn't know is I cut off the bottom part. And then they didn't get to see the time. This was at like, I don't know, 10 megahertz. So I really tricked them there. But, oh no, my animation's not working. Oh, it's slow, I forgot. Yeah. Anyways, I was running it this morning at 1.2 gigahertz, and we got a nice little output like this. What we are seeing is like charge injection when the switch closes. That gives you a little bit of a bump, especially you can see near the bottom here. So, but with the relaxed bandwidth, this would be like double the bandwidth that we need. We should be seeing considerably less of that. As for the whole topology, it's pretty simple. We just have an input buffer, then a switch, and then an output buffer. Randy, the member who's not here today, is working on the output buffer. Just so that he can drive a larger load than what we're currently doing. He made a really nice design last night, but he fell asleep at like 9 a.m. this morning, and he needs his 8 hours or whatever. So maybe if by the end I waste enough time, we could get to that. But yeah, that's my topology. And then Elliot's going to talk a little bit about like what we tried to do but didn't work.
Yeah, so this was another simplification of the topology that was probably oversimplified. And as you can see, the output looks a lot different from Gavin's and is definitely not close to what we needed it to look like. But this was also based on the original specs, which was, as Gavin said, a lot different from the relaxed specs that we have now. And then going back to the topology for a minute, which it's slow. Okay, yeah, it's just we basically took out the differential pair part in the middle, and it's a switch source follower design. I also don't have a lot of background in this, so I was kind of reading up on it, but it seems like for next steps, we're just going to be trying to optimize Gavin's design and fix the bumping issue that he's having.
Yes. We can do comparative study and then further if you have feedback on the ABC team in general after that, but we'll get to that.
Hi, Professor. Right, so I'm Pranav. I was working on the preamp and comparator block for the AEC. Why is not working?
It's a little slow. Good.
Okay. So for the AEC, we decided on a preamp and comparator design to take the input voltage and create the thermometer code output that is passed then to the encoder. So for the preamp stage, we decided on a differential amplifier with a cascode. And this takes a reference voltage from our resistor ladder that goes from VDD to ground, and then amplifies the difference between that each reference voltage and the input so that we get a larger difference that we can then pass to compare and get a cleaner reading with. So the differential amplifier, it's biased at 500 microamps. It's a pretty standard differential amplifier. That gets passed to a strong arm latch comparator that actually compares the outputs from the differential amplifier and then takes the output to the rail depending on if the input meets or exceeds the threshold voltage, reference voltage. I was running this system at 2 gigahertz. So I guess I could run it at the standard 1.2, or is it 1?
If
Yeah.
you do need your block to work faster than 1.2 because they all need to work
Yes.
together.
Yeah. Okay. Yeah, so on the side here, I also have some like resistors and capacitors just to represent the effects of the interpolation stages. So we're only going to have like one preamp for every roughly 4 reference taps on the resistor ladder. And then we're going to use interpolation resistors at the outputs of the preamp to pass to all 255 comparators for the 8-bit ADC. And that kind of looks a little bit like this, where you have the preamps and then you have the, this is for the positive output, but then we'd have another resistor ladder for the negative output, and that gets passed to each comparator. So here's some of my preliminary results. I managed to get a preamp gain of 6.35, which meets our kind of requirement of 6 dB. The bandwidth I was measuring after adding the comparator is like 455 megahertz, which is a little low, so we have to kind of get that up. Before adding the comparator and just kind of just testing the preamp individually, I was getting like 1.5 gigahertz. So I honestly don't know what I'm looking for feedback on like what I can do to kind of try to get that up and kind of change that. The latch time for the comparator is pretty damn good. That I ran this kind of block here across all the corners out over range of input voltages just to kind of get an idea of what it looks like across different characteristics. And this was kind of the result. The range ranges from like 48.5 picoseconds to 81.5 picoseconds. And the power for both the preamp and comparator are pretty good. The preamp at times and with various configurations testing out, I got up to like 1.8 milliwatts, but managed to get down to 1.4. And the comparators doesn't take too much power. I am not actually that confident if these values are right, but that's what I got. So, and that's it. Pretty much it. Any feedback, advice, questions?
Yeah, that's it for the ADC team. We have someone else working on FT, but she's reviewing that with Professor Swaybe. And so, yeah, if you have feedback on the ADC blocks, that'd be fantastic.
So sorry, I can't see your amplifier, your preamplifier very well, but you're saying it's a cascode, it's a differential cascode?
Yes.
Okay. And then how much gain you have from this?
6 dB.
Okay, 6 dB. And you have a 4-bit ADC or 5-bit?
8-bit.
Oh, you have 8-bit.
Yeah.
Yeah, this is not gonna work. You need higher gain here.
Okay.
Yeah, because just the strong arm latch needs probably about 50 millivolt or something at the input.
Okay.
And so the amplifier should have maybe a gain of I can probably a gain of 100, maybe 50 to 100, so that you can actually provide the resolution that the A to D needs.
Okay.
Right?
Yep.
So 6 dB is not going to cut it. It's not going to.
Okay.
Yeah. So it's an 8-bit. What is the are you trying? You guys are trying to design this A to D? Each one of you is designing a different part. Like one person is doing this, one person is doing that. Is it correct?
Yes. Yeah.
So you haven't really put everything together yet.
No, not yet.
Okay. Yeah, I think for individual components, definitely you want higher gain from your diff amp, from your preamplifier.
Okay.
I'm not too worried about the encoder, so that should be okay. What other components do we have?
It's the encoder and the track and hold.
Okay, so why do you need track and hold, basically? Do you want to keep the relative phase of I and Q with respect to each other because you only have one A to D?
I envision track and hold to give more time for preamp and comparator stage. It was my understanding that was standard in Flash APC. Is it possible without a track and hold?
So what you need is ADC can read any analog voltage. You don't have to hold it to. The only reason people do hold is because, let's say you have two inputs, I and Q. You want to use one A to D, so you want to kind of register them at the same time and read them later, right? Or, but otherwise, I don't, I have to look at the system because I don't really think that you need track and hold because you can have two A to Ds. But yeah, if you need track and hold, then you would probably need a multiplexer so that you can read I once, you can read Q. Are you putting this as part of the system, or this is just a test structure?
We envision that it would be on the GF chip, and if we have issues with the A to D implementation, we will be able to test the output of the RF front end using an off-chip ADC.
Right.
Yeah.
Yeah, so this would be essentially testing for future, because I think if you need fully digital output, then you would need you would probably need much more than just LVDS, or so I would just maybe send me the block diagram that shows the track and hold, because I want to know what was the purpose. Because if it is just one input, one output, you don't need track and hold. I don't think you do. Okay. So if this was inspired by certain implementation, please send that to me. Or that's why I say you have to have references everywhere, so that people can look at it and then give you good feedback. Otherwise, it's hard to provide good feedback. Okay.
Thank you.
Now continue designing. So don't give up the track and hold. There are, by the way, better track and hold designs than this, and you're going to suffer from this design because it will give you a lot of the kind of injection charge that especially at higher frequency is going to bother you. So look for better track and hold designs. Okay, but I'm just not sure if you need it, but yeah. Okay.
Yeah, absolutely. And yeah, I will take credit for the flawed ADC topology. That was something that I put together hurriedly and then handed off to the ADC team. That being said, I don't have the experience to justify that usually.
Yeah, so guys, Dolly, right? You can talk to Dolly about this. He would be able to help you with the overall design, what you need, what you don't need, and things like that. Okay.
Gotcha. Sounds good. That's pretty much everything we had, I believe. Yeah, thank you so much for your time. If you have any closing thoughts, concerns, questions.
I think so. You guys have done a lot of work. I really think that just starting from zero and getting to this point is a lot of work. I understand that, but just realize that a lot of the work is still to be done. So if you want to see, don't underestimate the layout part, post-layout simulation, putting everything together, running, overall simulation of the system. Those are very hard. Okay. So maybe finish this phase a little bit more quickly. Maybe, like I said, that's why, I think it's a good idea to shift everything to slightly higher frequency, because when you put them in layout, everything will be slightly slower. And then, the fun part is about to start. So I think this fun. If you guys want, we can continue doing this every now and then. And maybe I can give you feedback. Yeah. The other thing we could do is we have these presentation slots in our group meetings. Usually, sometimes we have somebody to present. Most of the time, we just cancel those presentations. Those are typically Thursdays at 3 p.m. I don't know if you guys are free, but you can get a lot of feedback if you can come to those presentations. If you send me your presentation, I guess you were recording it, so I can actually forward that to some of my students, and they can provide feedback because they know they're more knowledgeable than I am. So hopefully that would be good.
Yeah, that would be amazing. And I do think like not necessarily the scale of this meeting, but having like individual blocks, if they could come in and like do a quick presentation, get feedback. No, that'd be hugely valuable. I think we're definitely pushing to finish schematic work soon. And I think some blocks are closer than others. I'd say that from the perspective of the PLO, which is perhaps quite far away. But we're definitely pushing to really accelerate this project. And yeah, I think everyone here's done just a huge amount of work. So super impressed by everybody. Yeah, really thankful for all that.
Yeah. Do you guys have any timeline, like when you want to do tape out, or is it an open deadline?
June 17th.
June 17th.
June 17th.
So tape in June 17th for the RF and tape in July 7th for the digital.
Was it on June 30th?
June 30th for submission, July 7th final. It's realistically, I think if we don't shoot for that deadline, we won't hit the 1 in 6 months from then. But we are definitely pushing arguably unrealistically, but I think that's necessary in a way to make sure everybody like put the effort we need in. Yeah, to be transparent to the people in this room. Yeah. Do you think this will be done in 2.5 months?
It's doable, yeah. It's doable.
Yeah.
But it needs a lot of dedications. Guys, I have to go. But yeah, this was great. And yeah, I mean, I can definitely we can meet again once you have maybe start doing your layout and then bring the problems then. But do me a favor, maybe complete this presentation with for everyone. You can go and figure out which references you use. Just add the reference so that you know I can look it up and see what you're talking about. All right. Good luck.
Yeah. Thank you so much. Thank you for your time.
No
Take care.
problem.
Bye-bye.
Okay, so can everyone have sources put in the slides by end of day today? Barry, that should be quick, and then we'll send it to him. Yeah, we can even do it right now.
Should we do anything to like specify